Welcome to HP Tuners Subaru Training Part 9. In this training tutorial, we're going to take a look at our fuel injector characterization data. Now we need to go and program this in order to properly represent what injectors we have fitted into our fuel system are going to be to the Subaru ECU. So when we're translating what the fuel mass calculation is going to be into an injector pulse width, we're going to be representing that conversion based on the actual injector flow size as well as the response characteristics of the fuel injector. If we don't do this properly, we're going to have all kinds of fuel delivery problem to our engine. We want to avoid that. We want to be as accurate as possible. So we're going to learn how to program the data here in this training tutorial, also breaking down how the tables work and just understanding some of the fundamental concepts with injector data. We have a lot to talk about and cover. Let's jump into our tutorial so we can get started. Okay, so let's get started. We're going to be taking a look at how to properly program our fuel injector data and understanding the concept behind what the injector data represents within this tutorial. We have a lot to talk about and break down here. What we're going to be finding is that the injector data is going to be relatively simple to program. Some of the concept behind what's going on with the actual injector data, so something like our latency table or the short pulse width table, those concepts are a little bit foreign. We're going to go break them down here with some graphical plots. It should make a lot more sense towards the end of the tutorial as to why they're very important and how they fit together in our airflow and fuel modeling within the Subaru ECU. So the first thing I want to touch on is something we've talked about in our previous tutorials. That's going to be the relationship between fuel mass and air mass. Within an airflow modeled system, we're going to have an underlying equation that is going to help us determine how much fuel that we need to deliver into the engine. Now it's going to be fuel mass is equal to air mass divided by target air fuel. When we're dealing with our Subaru ECU, it normally is going to be a airflow model system that's based around a mass airflow sensor, although we can change it to speed density, again, as we talked about in our previous tutorials. But let's assume we're on a mass airflow sensor. It doesn't really matter if it's speed density estimating the airflow or measuring the airflow from the MAF. If we're actually measuring the airflow from the MAF, we'll be able to determine what the air mass is going to be. So we have established or would have established what air mass is going to be. And then we have a target air fuel table that's going to specify at a given load and RPM range of where we're operating our engine at, what we want the target air fuel to be. If we take our air mass and we divide it by the target air fuel, we'll determine what the fuel mass is going to be. Now, if we're dealing with the air mass in units of grams per second, the fuel mass would be determined in units of grams per second. Now, that fuel mass calculation needs to get turned into an injector pulse width, and that's going to be based on the injector size that we're dealing with. So a stock injector size of roughly 550 cc per minute, we're going to find that the injector pulse width that it converts to is completely different than something like an ID 2200 cc injector. The different size injectors have completely different flow rates, so therefore it's going to have completely different injector pulse widths. We need to calculate based on that flow rate size or the flow size of the injector that we have installed in our fuel system. That's the first type of basic conversion that we need to have applied in order to make sure we're scaling our fuel delivery proportional to that injector flow size. We also have a few other things that we need to keep in mind and to take into account. That's going to be the injector latency or the response time of the injector. And then we also have a short pulse width compensation that also needs to be applied that helps linearize a otherwise non-linear injector operation zone that improves the repeatability of our air fuel and makes sure that our fuel and airflow modeling is going to be stable and repeatable. So we have to break down how all of this works. Let's jump into that right now. So I have a 2018 Subaru STI calibration file open here. I'm going to go up here into the engine option, and then if we jump into fuel and then under fuel general, we're going to find that we have our injector data located right here under the injector control. Now specifically, we can find here we have our injector flow, we have a injector latency, we have a low pulse width, or also known as a short pulse width adder table, and then we have some of the details of how this is going to be applied. So the low pulse width minimum, the low pulse width maximum, and then there's also a low pulse width RPM limit, and as well as a minimum pulse width. All of these tables or data here fit together in order to characterize the injector that we're dealing with. Different brand injectors will have completely different characterization data that we have to program. even different size injectors within the same injector family or company. Thanks for checking out our teaser clip. If you want to see the rest of this video and more than 500 hours of current EFI training we have to offer, make sure you click right here. If you want to go and check out more teaser clips from this training course, click here, and you don't want to miss any of the videos we're going to be releasing on this channel, so make sure you subscribe and click here. Thanks for watching, and I'll see you guys later.